So, today we will have some details about the random waves, how it is described, what is meant by random waves, how it can be characterized, and how does the wave profile look when you take the measurements in the open ocean, and what do you do with all these measurements. So, this will be covered right from kind of fundamentals going up to the analysis of the random waves. As we have seen in earlier class, generation of waves in the ocean, that is because of the wind blowing over the water surface, and it basically depends on the growth of the waves, basically depends on 3 parameters: wind velocity, wind the fetch, the distance over which the wind blows over the water surface, and then the duration of the wind. This I have already mentioned about this, and this also I have mentioned, but I will just touch upon it again so that it is refreshed. So, somewhere in the deep ocean the wind starts blowing, and when the wind starts blowing you have short steep waves generated, and as long as the wind is continuously blowing over the water surface, the generation of the waves or the growth of the waves will continue, and the propagation will be towards the shore. So, when you talk about the waves, so let me say on the x axis it is a frequency, on the y axis let us have the energy. Energy is characterized by half into amplitude square. So, initially short steep waves will generate when the wind starts blowing, then it will continue so you see the peak being shifted towards the lower frequency area. So, that is within this shifting of the frequency, the energy, this is how the energy is being transmitted. So, initially you have the short steep waves generated, and slowly you will see that the lower frequency components dominate, and you see that the energy will be being shifted towards the low frequency, and finally you will have more or less, this is in general, you will have something like so as the waves are growing you call this as partially developed sea, partially developed sea. But how long it can keep on growing? It will reach a stage when the action of the wind no longer helps in the growth of the waves. When such a situation reaches, then we say that the sea is a fully developed sea, fully developed sea. So, we can have the partially developed sea somewhere here, characterized by lesser wind speed. So, each of this will be lesser wind speed or lesser duration. So, you can have a figure, this will be either for lower duration, lesser duration, or for lower wind speed. For either of these things, either of these two increases, you see that the shifting of the energy pattern more towards the low frequencies will get started, and then it will be a a gradual progressive towards the low frequency region, and unless until you get a situation where the fully developed sea is attained. So in this figure we can say that this is partially developed sea, and this is where you have the fully developed sea. This is in general the growth of the waves, and the growth of the waves these are all age old formulas, very old formulas, where they were using it as a function of just as an empirical relationship to get the wave height as a function of just a single parameter, that is the fetch. A fetch when it is greater than 30 miles and when it is less than 30 miles. And please note that this is H is in feet. This is one of the most oldest formula which has been widely used earlier for the prediction of a wave height directly from the fetch. It is not a function of any other parameter. Wave age, although we do not come directly from research point, I mean the design point of view, but wave age is the one which says it is the ratio of wave celerity to the wind speed, and this is wave age is a very significant factor in the phenomena of wind wave development, and we are talking only about wind waves. Okay. When wave age reaches a value of about 1.37, then we say that a fully developed sea is attained. There has been a number of studies by several investigators who have contributed to this wave growth, wind wave growth. I suggest if you are interested, read some of the books given under references. And it becomes very difficult for the wind to impart further energy to the waves. As I said, there is always an optimum limit up to which the wind is enhancing the growth of the waves, beyond which there will not be any effect. Within the fully developed sea, the wave age may be ranging anywhere between 0.1 to 2. So 0.1 more towards 0.1 would be the partially developed sea. There are other empirical relationships also, and these are all again very old formulas. For example, the maximum wave height is just controlled by, is a formula, you have a formula just controlled by wind velocity. The 0.026 into v square. The second one is including the fetch, and the third one gives the wave period, that is a function of velocity and the wind velocity and the fetch. No, please note the units for the different variables. Of course, these days this is not in much use, but nevertheless it is better we have all these formulas under our I mean when we deal with this kind of studies, it is better we are aware of such formulas that exist. These relationships are particularly useful when you are talking about short fetches and with dominating wind speeds, that is very high wind speeds, such as that you can find in that can occur due to hurricanes and storms, intense storms. So in general, why do you need to have information about wave studies, wave data studies? I have already given some kind of introduction in my introduction lecture, but again when you go into the finer aspects of wave data, these are exclusively important for the design of structures, design of ships, coastal processes studies, verification of wave forecasting, hindcasting models, wave energy computation, and there are a variety of other problems. when I say design of structures, it covers a host of structures in the coast, along the coast, as well as in the harbor structures. I am referring to all kinds of structures that is in coastal, on the coast, or in the deep ocean. So, for example, it is also wave study data information is needed for obtaining what is called as a scatter diagram. What is a scatter diagram? Scatter diagram is, for example, you have HS and HS and TP. For example, you have a number of class intervals for HS. Let me say that you have a class interval of 1, then 1.5, 1.5 to 2, etc., and then here maybe 6 to 7, 7 to 8, like this, okay. And inside this, with the measured data, you get all the values, how many waves with say maybe 10, 15, etc., say this is 9. So, from this you get how many number of waves has occurred in the month of January, or in the month of February, or in the month of March, etc., with a combination of wave height varying from 1 to 1.5 meters and wave period, associated wave period ranging between 7 and 8 seconds. So, like this you can have a scatter diagram which gives the percentage of occurrence of wave height and wave period. Why such informations are necessary, or we can talk about percentage of occurrence of wave height. For example, what is the percentage of occurrence of wave height less than or equal to 1.5 meters? If someone says it is 80%, then in the month of January, if someone is able to give me with the help of with the data analysis, after getting some figure like this, either a scatter diagram or a probability diagram, which we will see later, then I will be in a position to, and if he says that 80% of the time the wave height is less than 1.5 meters in the month of March, then, and if I am able to carry out specific operations in the offshore in the month of January in such a way that wave height, if it is less than 1.5 meters, all my operations can be done. If the wave height is greater than 1.5 meters, I cannot carry out any operations in the offshore. Then I will prefer January, and suppose in case if the month of February you have wave height percentage of occurrence greater than 1.5 meters, I mean less than 1.5 meters, equal to about of the order of say 50%, then you see that February is not so helpful compared to January. There is an element of risk involved. So, this kind of probability description of waves, or in terms of scatter diagram, helps us to also assess what is called as the weather window. The weather window, in the sense, I will try to have say January, February, March, like December, and my limiting wave height for the operations, for carrying out any kind of operations in the offshore, is again, as I said, is say around 1.5 meters, and if it happens for a particular site, this is 95, February 92, and March say 91, something like that, and maybe up to June it is okay, something less than 91, and suddenly from June to September, as in the case of east coast of India, you have a percentage of 1.5 meters, less than 1.5 meters is say around 40% only, approximately, or even less than 40%. Then I would prefer either I would be prepared to take a risk of for that 40%, because there is always an element of risk, because the percentage of wave height less than 1.5 meters has decreased. Then you have to be careful in planning your offshore operations. So, This kind of informations, this is only an example, and we might be able to see in detail when we are working out some problems, and this kind of informations are extremely important, and for which the wave data measurement and analysis are essential. Collection of wave data. Collection of wave data we can broadly classify it as indicated in the dark blue color, that is based on either visual observations, pressure sensor recording, or electrical devices, then ship measurements, buoy measurements, as well as stereo photographs and altimeter measurements. The first one is manual observation, that is visual observation. So you have a person standing along the coast looking into the ocean, and then using his eye judgment he will be able to assess what is the kind of order of wave height. So he can only give us the order of wave height, and usually this is done in harbors where they have some little bit of infrastructure for the personnel to stand along the coast, and that is what they do. Although it is not a reliable measure, and it also depends on the person who is doing this exercise, still it gives some kind of information about the variation in the wave climate. The other slightly better way of doing it is to have a kind of a marker, a graduated scale along an existing pier, which is quite common, maybe an existing jetty, and then you have a person who keeps on measuring this difference in the levels as the waves are moving up and down, and of course make sure that you need to include the tidal range. You have to apply the correction for the tidal range. That is one way of simplest but not accurate, but anyway it can give you some amount of information. The next one is the pressure sensor reading, where pressure sensors mounted in the flume, in the seabed, near the close to the seabed, can sense the pressure when the waves are propagating, and this pressure signals are sent to the onshore stations, and then which can be analyzed later. And remember earlier I had told you, when we looked at the pressures, dynamic pressures under progressive waves under the wave dynamics course, therein I had mentioned the importance of application of pressure sensors, because the basic tsunami pre-warning system is based on the pressure sensors, because it will, the moment the pressure sensor senses a long period wave like that of a tsunami, it is quite unusual, and immediately it can be made to trigger to the onshore station. So that is the basic kind of principle on which your tsunami pre-warning systems are working, and it is also very easy to have the pressure sensors mounted on some kind of a small pile in the near shore, in order to arrive at, in order to get the information about the near shore wave climate also. It is quite handy, and also the pressure sensors are also very useful for measuring the pressures, not only on in open ocean, but in the lab also you can use the same thing, and when it is mounted on structures, you use those pressures, those readings as the pressures exerted on structures due to waves, which we will be seeing later. Then comes electrical devices. Electrical devices, by measuring the change in the resistance or capacitance of a vertical conductor placed in seawater. So seawater is an electrolyte, all of us know. So when we place a gauge which is going to change either its resistance or capacitance when it is placed in water, the change in the resistance is being transferred to the data acquisition system, and then from that you can get the displacement of the water surface above a mean water line. So this principle is very this is the most widely used principle for laboratory measurements of ocean waves, laboratory measurement of waves. So it is either based on the principle of change in resistance or change in capacitance. Then comes ship measurements. By measuring pressure at a point on the hull to give wave height relative to the ship, this is one way of doing it. And also in the under the ship measurements, you also can have some kind of observers, either trained observers or untrained observers, to continuously not continuously, at least on a daily basis, few times in a day they keep finding out what is the approximate wave height, etc., wave characteristics in general. But these wave data may or may not be directly useful to us for the simple reason these wave characteristics are available only in the ship route, along the ship route. So, and then comes the buoy measurements. Buoy measurements is the most widely used, particularly for major projects. They are going for buoy measurements. This is just using the vertical accelerometer mounted in a buoy floating at the sea surface. You can have either directional wave rider buoy or directional wave rider buoy. So, and there are other host of parameters that can be measured with the help of a buoy, apart from the displacement of water surface. And this is more commonly used, the buoy measurements are most commonly used and more accurate, and there is absolutely no problem. There is a problem with the buoy measurements, because you have this particularly when it is mounted in shallow water, the cutting off the mooring lines, because the buoy will be something like this, it will be moored to the sea floor. So if this is cut, then you know what happens, your buoy disappears and the entire exercise of trying to measure the wave climate is lost. Apart from this problem, there is not much of other technical problems with the measurement of the wave climate using a buoy. Finally, the spatial information on waves can be obtained by stereo photographs, and also by taking records on the sea surface using altimeter mounted on aircraft or through satellite. This has become very common these days, that there are a lot of institutes which have been working in this area, because you do not need a big laboratory or etc. To investigate to work on this work in this area, and there are lot of things to be done using this, and these are more or less more or less quite good. The results, the information you get is quite useful. A number of studies have been carried out in order to prove that the results coming out from the altimeter measurements etc. is quite genuine and quite reliable. So that gives us a overall impression about the wave data, the importance of wave data, and how you can what are all the means of measuring the wave data. But before coming into the regular waves, before coming into the random waves, what did we see? We took a regular wave and tried to analyze what happens when a wave with a particular wave height and wave period propagates in a water depth d. See, we looked at the pressure, salinity, then the power, energy, etc., and then we looked at the whole thing. This is in order to get the information of the wave characteristics by just considering one single frequency wave. But in the open ocean it is not like this, and try to recollect when I presented the basic wave dynamics. the ocean surface will not look like this. You can never have a regular sinusoidal wave moving in the ocean, but instead the surface elevation will be like what you look on the screen, and this is a random wave, and this is how it would look like. And when you have a random wave like this, what do? You cannot have such a long record and just how do you describe? There should be a way or means to express the characteristics of such a long random wave. So the usual common method is to obtain what is called as the spectral density or the distribution of energy. So as you know, the wave has two parameters, one is wave height and wave period or frequency or 1 by f, okay, frequency or the time period. So this is how it would look like, and on the right hand side you see that if you subject the random wave, you should be able to get what is known as a spectral density plot. What exactly is a spectral density? Spectral density gives nothing but the distribution of amplitude square as a function of frequency. So for example, you will have a wave period, as I said, say for 5 seconds, from 5 seconds to 20 seconds. So this will be 1 by 20 to somewhere 1 by 5, and this is the area where you are likely to have your distribution of energy. So at each frequency you will now know what is the amplitude square. Half amplitude square is nothing but the energy. After all, the time history on the left hand side which you see is due to the superposition of a number of sinusoidal components of different frequencies and maybe same amplitude or different amplitudes, like this. There are different frequencies. You please refer to my earlier lecture where I had shown some slides by superposing a number of sinusoidal components. Now here this is how you try to generate a random wave, but now if you have a random wave which is measured in the field, what you do is you try to arrive at the information as shown here, that is through a plot called as spectral density plot. So if you have this, I can always say what is the frequency of maximum energy. This is the maximum energy. What is the maximum energy? What is the frequency at which the maximum energy could occur? What is the range of frequencies? See, for example, this is the range of frequencies over which you will have the energy being distributed. So all this kind of information can be obtained, more we will see later. So how long should be the measurement? How long should be the measurement? Just because you have an instrument that can measure the wave climate or the displacement of the water surface about a mean, can you keep on continuing the the measurement? So what will happen? You will have a voluminous data. So there is a kind of a compromise you should need. So the accuracy of any statistical analysis of the data or a random variable like eta increases with the sample size, that is right. If you want to have the more number of waves, the sample size will increase, but the computation time also, I mean the number of waves you are going to deal is also going to, you will be having a lot of data. So Cartwright, he mathematically has analyzed and he has said this is how the standard error will look like by increasing the number of waves. So based on this, it was suggested by several investigators in the past that a minimum of 100 waves could be considered for the analysis. A minimum of 100 waves could be considered for the analysis in order to obtain the average wave characteristics or the energy distribution in the random wave. Is that clear? So the standard practice is to measure the wave climate for a duration of 20 minutes, duration of 20 minutes duration continuously. How frequently you need to measure? Again, just because you have a continuous recording equipment, you cannot keep on recording. So you measure once in 3 hours. What is that once in 3 hours? The assumption is that the basic statistics in the ocean, in particular for the waves, will remain more or less same, at least for a duration of 3 hours. So you consider 3 hours duration. So for 24 hours, that is for one day, you will have 8 records, typically 8 values of significant wave height and period. Having seen the basic information about the random waves, let us move on to methods of wave data analysis. Broadly, you have two procedures. One is the statistical method, the other one is the spectral method. Both these methods are quite straightforward. Both of them give lot of information about the wave characteristics that are needed for the design of structures. In the case of statistical procedure, the individual waves are defined by 0 up crossings or 0 down crossings. The unit of analysis in this case, in the case of a spectral method, is trying to extract the values of eta at a fixed time interval. So you digitize, this is how a random wave look like, a portion of the random wave. So at regular intervals, so this is a delta t which should be maintained constant. At delta t you digitize the displacement of the water surface about a mean line. So you will have positive, 0 as well as negative values. See, usually most of the cases the probability density of the wave elevation, that is probability density, I am sure many of you know, if not you need to look into the basic statistics book. The probability density function of a wave elevation is found to be mostly following a normal distribution or a Gaussian distribution. If you refer to books, they will also use that wave elevation is a Gaussian process. That means it follows a normal distribution or it is a Gaussian process. This is more or less true when you are having the measurements in slightly deeper waters. But when as you come closer to the shallower waters, as you know the waves become steeper, it starts filling the bottom and becomes steeper. There is always a kind of unsymmetry or the asymmetries in the wave profile, and hence the probability distribution of eta may slightly deviate from normal distribution. So when I say eta will have positive as well as negative. Please remember that here we are talking about a Gaussian distribution where sigma is the standard deviation and x bar is the mean, and x will be taking a value anywhere between minus infinity to plus infinity. When I say eta or the wave elevation can be both negative and positive and of course 0. But when I say wave height is usually, what is the definition of wave height? When we talk about a regular wave, this is the distance between the crest and the trough. So wave height always has a positive value. But here also we have eta, where eta can have positive, negative or 0 value. So it is more or less most of our locations in the offshore, more or less it will be following Gaussian distribution. So when you have a measured wave elevation, you are supposed to check whether it follows a Gaussian distribution or otherwise, because later you will see that in literature you should refer to some additional literature more about the formulas that are applicable that can be applied once you know that eta follows a Gaussian distribution. So methods of analysis of ocean waves, statistical method and the spectral method, as I have mentioned earlier. The statistical method can be categorized as the zero up cross method and the zero down cross method, whereas the spectral method can be classified as that obtained through fast Fourier transformation or covariance method. Earlier it used to be a bit tricky in order to get the spectral density, but these days you have a number of softwares, standard software, or even in the lab MATLAB you can easily get all this information. So the software that uses that is widely used for the spectral analysis is the WAFO, and those who are working on MATLAB, please think of this WAFO, and that gives you, that is quite handy for solving the problem related to fast Fourier transformation, I mean to get the spectral density. The covariance method was used earlier, but these days they are not using it because that is a bit cumbersome. So statistical method, under the statistical method the waves, individual waves are can be obtained using the zero up cross method or the zero down cross method. How do you get that? How do you separate that? Because I have a separate, I have another slide which shows the same thing, but I feel that it is better I explain with the help of this. So let me explain this 0 up cross method and the down cross method with the help of a portion of the wave record which we have got. So wave recorder may be a long one, so I am just taking a portion. So this is where, this is the mean water line and this is where it is moving in the upward direction, and the next point where it crosses the mean water line is somewhere here, and the next cross section is somewhere here. So now we see that this is your first wave, for example, and this is the wave height 1 using up cross method. This is the wave period using up cross method. Similarly here I will have this as HU2 and TU2. So this is how you can do for the entire record and obtain the get the individual waves, characteristics of the waves like wave period and wave height through the up cross method. Now this is where it crosses in the downward direction, and then we call this as down cross method. So in this case this will be your HD1 and this will be TD1. Similarly here this will be HD2 and this will be TD2. So like this, as I said earlier, for a good representation of the wave characteristics from a given record, you should cover at least a minimum of 100 waves. So I have the individual waves which can be H1, Hi2, I equal to 1 comma n Hi and Ti. Is that clear? So I can have, as I said earlier, n will be, should be greater than or equal to 100. So you have enough number of data, then from which you can obtain the statistical measure of the waves, and also we can talk about the Rayleigh distribution. As the wave profile, wave elevation follows the Gaussian distribution, and in most of the cases if it follows a Gaussian distribution, I mean the wave elevation, the wave height is also expected to follow a Rayleigh distribution. A Rayleigh distribution is given, so I will remove this. So it is also available in the lecture material later through a slide. So once you have got the individual wave heights and the wave periods, you can arrive at the probability density of the waves. That is, when you have the 100 or more than 200 or more than 100 values of the wave heights, using the simplest statistical way, you can obtain the probability density of the measured wave elevation or the percentage of occurrence of different class intervals of the wave heights for the measured values. So now you have a Rayleigh distribution which is given as shown here. It is a single parameter distribution which is just a function of h bar. What is the advantage of this? What is the advantage of saying that I have found that of Chennai the wave height is following a Rayleigh distribution with an average of 1.5 meters in the month of June. So what am I talking about? In the month of June, if I am able to say only after proving that the wave height is going to is following a Rayleigh distribution, if I have already proved, then I have the liberty of saying if the June month mean wave height is 1.5 meters, I can always say that in the month of June the wave height follows a Rayleigh distribution of Chennai coast. So then the whole lot of information I can get, okay. So like what is the percentage of occurrence, I mean what is the probability of wave height less than or equal to 1 meter, what is the probability of wave height less than or equal to 2 meters, all this information you can get once you have proved that it follows a Rayleigh distribution. Otherwise you need to do that only with the measured probability density. For doing this, for understanding this kind of information, it is enough you have 1 year data. These are also referred to as short term wave statistics. For short term wave statistics 1 year wave data is good enough, and mind you we are not talking about the design wave height, we are not talking about the design wave height, this is for maybe operational wave conditions, you can say as operation wave conditions. So if you draw the probability density, you will generally know what is the kind of wave climate that exists of a particular site during the different months. Apart from the widely used Rayleigh distributions, there are other standard distributions for explaining or for discussing about the distribution of wave heights. One such distribution is the Weibull distribution. What does the Weibull distribution? This Weibull distribution is very important or explains the distribution of waves, wave heights, mostly in shallower waters. As I said, the waves steepen near the coastal waters. This kind of this distribution has been found quite useful. Here you are provided here all this parameter, this is nothing but the wave height, and you have the beta parameter is nothing but the hi into the frequency of wave height, the whole thing, that is going to be the beta, and below is the one which is alpha, this is gamma function of 1 plus alpha 1 by beta and divided by the h bar. So once you evaluate the beta and gamma, use this distribution to get the probability density function. Weibull distribution becomes a Rayleigh distribution if beta equal to 2 and alpha is equal to 1 by HRMS square. HRMS is nothing but the root mean square value. With the help of a problem we will be able to understand all these things. There are other types of distributions which are called, one is called as the Glukhovsky distribution, which takes into effect the water depth. The expression is quite long and it is not that widely adopted, it is compared to Weibull distribution or the Rayleigh distribution. This is only for general information that this expression can be used where you are talking about waves in very coastal, I mean in the near shore area. So here H star which is included there is H by water depth, the water depth is brought into picture. So with this I conclude the basics of the wave statistics and then we will proceed again.